I just realized that my recording got cut off. The sound got cut off because my microphone got muted by mistake. So I'm going to go over this once more. So we have the sum rule. The sum rule basically states that if you're taking the limit of a sum of two functions, then you could take the limit of each function independently of one another and then add up their limits. Similarly, for the difference rule, if you are finding the limit of a difference of two functions, then you could take the limit independently of each function and then subtract those limits from one another, and vice versa. So if you begin with something like this, subtracting the limit of two independent functions and they are both approaching the same number, then you could combine them. We have the constant multiple rule, which is going to play a very important part in the semester, especially as we move forward with derivatives. It's going to come in handy to know this, which basically states that if you're multiplying a function by a constant while taking the limit, then because this constant does not depend on x, you could pull it out from the limit computation and simply compute the limit of the function, and whatever you get as the limit, you multiply times c and you get the same result. For the product rule, we have that if you take the limit of a product, then it is the same as taking the limit of each function independently and then multiplying those limits together. Similarly, for the quotient rule, if you're taking the limit of a quotient or a ratio, then you could take the limit of the numerator and then take the limit of the denominator and then divide the limit of the numerator by the limit of the denominator, and you will have the same result, provided that obviously the limit of the denominator is not equal to 0. Because remember that if the denominator equals 0, then we have undefined situation. The ratio is undefined because we cannot divide by 0. Now for the power rule, and these are n's, so my n's kind of look like h's or u's in this case. I feel like they look like u's now, but they're n's. So it's basically saying that if you take the limit of a function and that function is raised to some power, and that is the same thing as first taking the limit of the function and then raising that limit to the power. So you have a choice here. Sometimes it is easier to find the limit first of the underlying function and raise that limit to the power. Other times you may find yourself simply raising the function to that power and then taking the limit. And similarly to the power rule, for the root rule, we have that if you're taking the limit of a function and then you're taking a root of that function, that is the same thing as first finding out what the limit is and then taking the root of that number. This provided that the function is positive for x values near a, and if n is an even number, so n is even in this case. So that was just some of the last things that were cut off from the recording. Alright, so let's continue. Let's do a couple of examples applying these rules. Okay, so we have example. So let's see what we can do. And let me detach this once more. Okay, so examples. Suppose the limit as x goes to 2 of f of x equals 4, the limit as x goes to 2 of g of x equals 5, and the limit as x goes to 2 of h of x equals 8. Okay, so we're going to use some of these rules to evaluate these limits, and the first limit that we will evaluate is the following. I'm going to take the limit as x goes to 2 of the difference quotient f of x minus g of x divided by h of x. And this should look a little familiar to you because in your pre-calculus class you should have seen the difference quotient be applied. So this looks very similar. Well, this is a difference quotient application right here. So by my rules here, I notice that I have a quotient and I have a difference, hence the name difference quotient. So the first rule that I'm going to apply will be rule number 5, because I have a quotient. So by rule number 5, we have the following. We have this. So we have the limit. So this is equal to the limit as x goes to 2 of f of x minus g of x, all divided by the limit as x goes to 2 of h of x. So this is by rule number 5. Now by rule number 2, the difference rule, we have that this is also the same as the limit as x goes to 2 of f of x minus the limit as x goes to 2 of g of x divided by the limit as x goes to 2 of h of x. Now, why is this important? Well, here, there's nothing that I could have done in this first step. I have no idea what f of x is, I have no idea what g of x is, and I have no idea what h of x is. What I do know is I do know that the limit of f of x as x goes to 2 is 4, the limit of g of x as x goes to 2 is 5, and the limit of h of x as x goes to 2 is 8. But here, I cannot simply do the substitution because these are the actual, right here we have the actual functions. So we did some manipulations by using the rules so that we could actually get to see and apply the limit to each function. But now I actually do know what the limit of f of x as x goes to 2 is. That is 4. And I do know what the limit of g of x as x goes to 2 is. That is 5. And the limit as x goes to 2 of h of x is 8. So what we have here is we have 4 minus 5 over 8. Well, 4 minus 5, last time I checked, that's negative 1. And 8 just stays the same, so we have negative 1 over 8 as our limit. So the limit as x goes to 2 of the difference quotient g of x, f of x minus g of x over f of x over h of x is equal to negative 1 over 8. And again, this is just an application of 2 of the rules that we now have. So let's do another one. What about limit as x goes to 2 of 6 times f of x times g of x plus h of x? Well, here we have 3 rules going on. We have the product rule, we have the sum rule, and we have the constant multiple rule. Now, it is important that you understand which rule you should apply first. Here, the first rule that I would apply first will be the sum rule. Why? Because if we think back, this looks like a binomial. This is one term, this is another term. So it makes sense to first split those up first. So that will mean that we have limit as x goes to 2 of 6 times f of x times g of x plus limit as x goes to 2 of h of x. This is by rule number 1, the sum rule. Now, by rule number by rule number 4, the product rule, I'm going to separate the product on the inside. So that's the same thing as limit as x goes to 2 of 6 times f of x. It doesn't really matter where I put the 6, whether I keep it with the f of x or the g of x, times, because by the rule I have a times, limit as x goes to 2 of g of x plus limit as x goes to 2 of h of x. I'm just carrying that one over. And this is by rule number 4, the product rule. Finally, by rule number 3, the constant multiple rule, I can pull out this 6 from in here because that's just a constant. So this is the same thing as 6 times limit as x goes to 2 of f of x, right, times limit as x goes to 2 of g of x plus the limit as x goes to 2 of h of x. And again, we know, and this is by rule number 3. So by rule number 3. And again, we know now what the value of the limit as x goes to 2 of f of x, of g of x, and h of x. So from before, we know that the limit of as x goes to 2 of f of x is just 4. So it's going to be 6 times 4. And then g of x was 5, so times 5. And then h of x was 8. That limit was 8, so plus 8. So now we have 6 times 4, I believe that's 24. We have 24 times 5 plus 8. Now 24 times 5 plus 8, I believe 24 times 5 is 120, and plus 8, that will be 128. Once again, this is yet another way of applying, another example of applying our rules for finding limits analytically. Finally, let's just do one more. Let's find the limit as x goes to 2 of g of x cubed. So here we will apply rule number 6, the power rule. So rule number 6 says that if we have the limit as x goes to some power g of x cubed, this is the same thing as first taking the limit of the function and then cubing that limit. So the limit as x equals to 2 of g of x was 5, and 5 cubed, I believe, is 125. So this makes our life much easier because we do not, remember, we do not know what g of x is by itself. So we cannot cube it because we have no idea what that is. So this makes our life, but we do know what the limit as x equals to 2 of g of x is. So this makes our life much easier when situations like this arise. So now we will move on, now that we have these tools under our belt, and we will expand our knowledge of how to compute limits away from linear functions and into polynomial and rational functions. So it's the limits of polynomial and rational functions. Oops. What happened? Functions. Okay, so we can now see how the limit laws are used to find the limit of polynomial and rational functions. For example, what if we have the following? What if we have the polynomial function p of x equals 7x cubed plus 3x squared plus 4x plus 2. And we want to find the limit at some arbitrary point A. Okay, so if we wanted to find this limit as x goes to that arbitrary point A, what we really are saying is the following. We're trying to find the limit as x goes to A of p of x. But we know what p of x is, so we could substitute it into our expression. So we have limit as x goes to A of what p of x is, which is 7x cubed plus 3x squared plus 4x plus 2. Now, by our laws of limits, we see that we have a sum. All of these monomials are being combined or added together to form this polynomial. So we could separate them individually. So what we have here is the following. We will have the limit as x goes to A of 7x cubed plus the limit as x goes to A of 3x squared plus the limit as x goes to A of 4x plus the limit as x goes to A of 2. Now remember this by the sum rule. So by rule number 1. Now that is the same thing as the following. By rule number, I believe it's number 3, the common multiple rule, I can now pull out this 7, this 3, and this 4 outside of the limit computation. Why? Because they're just constants. So I can actually pull them all out. So what I have here is the following. I have the limit, well, I have 7 times the limit of x goes to A of x cubed plus 3 times the limit so x goes to A of x squared plus, and honestly I could really combine these two because the 2 is by itself and the 4x is by itself, so I could actually combine them. I could keep them combined, so I will have limit x goes to A of 4x plus 2. It doesn't really make a difference whether I have them separate or not, because the limit as x goes to A of 2 is just 2, so I could just keep them combined. And this is by rule number 3, by the constant multiple rule, that we can pull out these constants out to the outside. Now in the same note, by rule number 6, the power rule, I could pull out the exponents from within. So these exponents, the 3 and the square, I could pull them out. So I have 7 times the limit as x goes to A of x cubed plus 3 times the limit as x goes to A of x, the whole thing squared, plus limit as x goes to A of 4x plus 2. Now finally, this is something that you should notice right away, but if you don't, that's okay for now, but in the future you should definitely notice. These are all linear functions right now on the inside. They are all linear, and we know from earlier today, from part 1 in this video, that to evaluate the limit of a linear function, all we have to do is plug in the value that we're limiting to into x. Well, that happens to be A, because we are taking the limit as x goes to A. So we could plug in A for every x that we have here, and this is what we have. This is what we will get. We'll have 7, and the limit as x goes to A of x is just A, so this is A cubed plus 3 a squared when you plug in plus 4a plus 2. And this is by the theorem. So this is by theorem of limit of linear functions. We could simply plug in. But here, notice that 7a cubed plus 3a squared plus 4a plus 2, this is the same thing as p of a. It's the same thing as taking the function that we originally had and substituting a for x and evaluating it at a for each value. So what does this mean? This means that in this whole equality, this means that the limit as x goes to a of a polynomial function is simply the polynomial evaluated at the limiting value. So much like linear functions, the limit of a polynomial function is found by direct substitution. So note, much like linear functions, the limit of a polynomial function can be found by direct substitution. That is, once again, the limit as x goes to a of p of x equals p of a. And we discussed this earlier in the semester during the second lecture, actually the second and third lecture, that when the limit exists, the limit could be the output value of the function, or it could be a different value, or obviously it could just not exist. So we have those three situations. So this should not be of surprise because I kind of spoiled it. So now it is actually not that difficult to evaluate rational functions. So from this result, we will see that it is not so difficult to find the limit of rational functions. And if you remember pre-calculus, this should make sense. So, for example, if given a rational function of the form, and by definition from pre-calculus, the form of a rational function is the following: f of x equals p of x divided by q of x, where p and q are both polynomials, then by applying rule number 5 of limits, and this was the quotient rule, we have the following. We have that f of x, well, the limit as x goes to a of f of x equals the limit as x goes to a of p of x over q of x, because that's what f of x equals, That, by rule number 5, is the same thing as the limit as x goes to a of p of x divided by the limit as x goes to a of q of x. But guess what? P of x is a polynomial, q of x is a polynomial, and by the work we did up here, we know that by using direct substitution, we can get what the value of the limit is. So that's just simply going to be, if we wanted to evaluate the limit of p of x as x goes to a, we simply substitute a into the function, into the polynomial. So that will just be p of a. Similarly, if you wanted to evaluate what the limit of q of x is as x goes to a, then you simply substitute into the polynomial a. So that's q of a. So what we're saying is that the limit of a rational function is simply, once again, solved by using direct substitution. So the TLDR basically says the following: the limit of rational functions are also evaluated please don't crash on me, evaluated by using direct substitution. And that leads to the following theorem. So theorem, this is the limit of polynomial and rational functions. It says the following: assume P and Q are polynomials and A is constant. So A is a real number, it's a constant. Then we have two situations. Situation number 1, for polynomial functions, the limit as x goes to a of p of x equals p of a, and for rational functions, the limit as x goes to a of p of x over q of x is simply p of a over q of a, so long as q of a is not equal to 0. Again, cannot have 0 in the denominator. So this is something that you should always keep in mind. Alright, let's go, I guess, back up. Continue on this side. They seem to have run out of space in the bottom. Okay, so let's do an example. So let's find the limit of a rational function. So let's say we have limit as x goes to 2 of 3x squared minus 4x divided by 5x cubed minus 36. Well, the first thing you need to be concerned about when dealing with a rational function is that the denominator cannot be 0. So we first have to check for that. We have to check that the denominator will not be equal to 0. So let's see, we have 5. When we plug in 2, that's going to be 5 times 2 cubed minus 36. So 2 cubed is 8. So 5 times 8 minus 36. I believe 5 times 8 is 40. So 40 minus 36 is equal to 4. And 4 is not equal to 8. So denominator is non-zero. So we're good. So you should always check that. That should always be your first step. Okay, so now we can now use the fact that there's a rational function, and we could just plug in. So we have that the limit of 3x squared minus 4x over 5x cubed minus 36 is simply 3 times 2 squared minus 4 times 2 divided by 5 times 2 cubed minus 36. So 2 times 2 is 4, so we have 3 times 4 minus 8 over, we already calculated this, so this will be just 4. But 3 times 4, I believe that's 12, so we have 12 minus 8 over 4, and this is going to be 4 over 4, which last time I checked, that equals 1. So we have the limit, and technically, you know, I'm saying equality here, so the limit, it's always good to rewrite this, the limit of x as x goes to 2 of 3x squared minus 4x over 5x cubed minus 36 equals 1. Okay? Good. Right, so let's do another one. So let's do another example. EX, I don't know if I already introduced it in this class, but when I write EX, that just stands for example. So let's evaluate the following limit. So evaluate the limit, again as x goes to 2, of 2x cubed plus 9 under the square root plus 3x minus 1, all divided by 4x plus 1. So again, I always say check two things. Here we have two things to worry about. If you remember from pre-calculus, we have domain issues on a fraction. So if you have a fraction, so recall, if you have a fraction, a over b, then b cannot be 0. And if you have something like square root of x, then x has to be greater than or equal to 0. So we have to check both of those things before we even, well, as we begin with the problem. So the denominator we could clearly see is not going to be 0 because we have 4 times 2 plus 1. That's going to be 9. And we have a positive number getting cubed and then adding it to another positive number. We could see that it's going to be also non-zero. If you take 2 and then plug in 2 and cube it and then add 9, all of those things are positive, so we're not going to have a negative number in there. So we can proceed on, and by the theorem, we'd actually just plug in. So we can simply just plug in 2 wherever you see an x and do the computation. This minus 1 divided by 4 times 2 plus 1. So what we have here is that we have 2 cubed, so it's going to be 2 times 8 plus 9 plus 6 minus 1 divided by 9, which we already checked. 2 times 8 is 16. 16 plus 9 is 25, so we have the square root of 25 plus 5 over 9. Square root of 25 is 5, so we have 5 plus 5 over 9, so that's 10 over 9. And that's all she wrote. That will be the limit of this problem right here. Okay, so we will say if you notice, the limit of this function as x again goes to 2 is the same as the function evaluated at 2. Function evaluated at 2. Now here we had to be a little bit more careful because the numerator is not a polynomial. If you go back to your pre-calculus notes, a polynomial does not have roots like this, fractional roots, or rather fractional exponents. Okay. All right, so we have to worry about one more thing talking about when talking about limits, and that is one-sided limits. So the theorems for linear functions and polynomial functions hold for left and right sided limits. So if you were taking the limit from the left or the right, or the right of a polynomial function or a linear function, then you will get a result. So what I'm saying is these theorems are valid. These theorems are valid if you replace limit as x goes to a with limit as x goes to a from the right side and or limit as x goes to a from the left side. The laws of limits from 1 through 6 also hold for one-sided limits. Okay. Now, however, rule number 7 has to be modified. So remember, we had 7 rules. I told you when I introduced them that technically we will have 8 because rule number 7 we will modify. So notice rule number 7 has to be modified slightly for one-sided limits. Okay? So here's what we have. So this is another theorem. That's why I said that I was going to be abbreviating this word. And this is the limit laws for one-sided limits. And it says the following. First of all, as I just mentioned, laws 1 through 6 hold true for one-sided limits. So we don't have to rewrite them again. We simply replace limit x goes to a with limit x goes to a from the right side or limit x goes to a from the left side. Okay. Now law number 7 is modified as follows. So for rule number 7, which was the rule about the roots, we have the following. Okay, so we have 1. If we're taking the limit as x goes to a from the right side of f of x to the power 1 over n, this is the same as taking the limit as x goes to a from the right side of f of x first, and then taking the root, provided that the function values are bigger than or equal to 0 for x values near a and x bigger than a, or rather I should say with, not and, I have two n's there, with x bigger than a and n is even. And this is important because remember, when we're looking at the limit to the right side, we're looking for values bigger than our a, because the bigger values occur to the right side of a on the number line. And number two, we have that the limit from the left side as we approach a of f of x 1 over n is equal to the limit as we approach a from the left side of f of x all raised to the power 1 over n, again provided that this time they won't change, so the function value will stay positive. They will stay bigger than or equal to 0 for x values near a. But the one difference here is that x is going to be less than a, and this is if n is even, if again n is even. So this is the difference here that we didn't have before. In the previous rule, we didn't care whether x was bigger than a or less than a. In this particular definition of the rule, we do care whether x is bigger than a or x is less than a. Okay? So let's do an example. So calculating left and right side limits. So let's say we're dealing with the following piecewise defined function. So let f of x equal negative 2x plus 4 if x is less than or equal to 1, or f of x equals the square root of x minus 1 if x is strictly bigger than 1. Now what we want to do is we want to find the limit as x goes to 1 from the left side of f of x. We want to find the limit as x goes to 1 from the right side of f of x. And finally, we want to stay whether they exist or not. So sometimes these limits may not exist. Alright, so let's deal with the first rule, x is less than or equal to 1. Well, if I'm looking for, let's see, so let's say the limit, I'm looking for the left-sided limit. So let's say x is going to 1 on the negative side of f of x. Well, if I'm coming from the left side of 1, that means that I'm less than 1. So that means that I'm using the first rule. So I'm using this one because I'm less than 1. So that means that I'm really looking for the limit as x goes to 1 from the left side of negative 2x plus 4. And since we're coming from the left side, and this is a linear function, I can simply substitute. I can use direct substitution to solve this. So what I'm going to do is I'm going to plug in 1 where I see an x. So I'm going to have minus 2 times 1 plus 4. Minus 2 times 1 is minus 2, and 4 minus 2 is 2. So we have that the limit from the left side is simply 2. Now, for the other limit, for the other side, so for x bigger than 1, first of all, notice that if we subtract 1 on both sides of this inequality right here, if you subtract 1 from both sides, what will you have left is we will be left with the inequality x minus 1 is bigger than 0. So it's strictly bigger than 0 at that. So we know that the inside of the rational function, or the rational expression that we have, is not going to be equal to 0, because whenever x is bigger than 1, this is always positive. So we have that the limit as x goes to 1 from the right side, of f of x is going to be equal to the limit as x goes to 1, again from the right side, of the square root of x minus 1, but again by the rule that we just defined, rule number 7 for one-sided limits, which was this one. Here we have that x is bigger than 1, so we're using this rule right here, the top one. We have the following. This is the same thing. I'm just going to rewrite it. This is the same thing as limit, so you can see it better. So x is 1 from the right side of x minus 1 to the power 1/2. So maybe that will help you see what's going to happen better. And the rule says that I could simply take the limit first. This is why this is so useful. I could first take the limit of the inside and then apply the outside, apply the root. But now if I apply the limit on the inside, notice that this is now a linear function instead of being a root or a radical. So I could simply just plug in 1. But if I plug in 1, 1 minus 1 is going to be 0. And 0 to the power 1/2, it's still 0. So we have now that the limit as x goes to 1 from the left side of f of x equals 2, and limit of as x goes to 1 from the right side of f of x equals 0. So therefore we know 0 is not equal to 2, so this means that the limit as x goes to 1 from the left side of f of x is not equal to the limit as x goes to 1 from the right side of f of x, which means that the limit as x goes to 1 of f of x does not exist. Remember, for the limit to exist, both the left side and the right side limits must be equal. If they are not equal, then the limit does not exist. I'm going to cut this video here and pick it up on the next one.